Welcome back all of you. In the last class, we discussed about phases of the RF pulses and what happened to the magnetization by applying 90-degree pulse along x-axis, y-axis, and how we detect the magnetization, how we can take the magnetization, we can make it a completely process about a particular axis like XZ plane or YZ plane like that. You can make it a process in a particular plane completely by 360 degree. And then when we apply the 90-degree pulse, we also discussed, I said, initially there is a statistical coherence. Okay, temporary statistical coherence of all the magnetic moment vectors which get aligned along the detection axis in which you are detecting, where you have kept your receiver. Now, what happens to this coherence with time? That's what we started discussing. That's where we ended the last class. The spins interact with the surroundings. The spin vectors start dephasing and keep rotating in the XY plane. What happens? As soon as you bring all the spin packets along from Z axis to X axis like this, initially they will be like this. Then one will start like this, one will start like this, they will start moving like this. Okay? Slowly. They start moving like this, these spins start moving like this. Faster move, slow moving components we call. When all these spins are aligned along this axis, where you have kept your receiver, initially, immediately after applying the pulse, the signal intensity is maximum. But what happens as you go with time? That we will see. Initially, all the signals are, all the magnetic moment vectors are here. It is a vector coaddition. So there is a maximum intensity. That's fine. Now, this temporary statistical coherence is created like this. The temporary coherence, all these vectors are here. But they are independent magnetic moment vectors. But you have created the coherence by 90-degree pulse. So what will happen with time? They will start decaying like this. That's what I said. So initially they will move like this, some of them will move like this. And slowly after some time, there is a complete decoherence. Now if I have a detector here, receiver is here, the magnetization is not full now. Because different components are there. Then you have to resolve into a component along x-axis and y-axis, and you get only magnetization pertaining to this component along this axis. So the sum of vector addition of the components is not maximum. It has to come down. So its intensity will decay, but it undergoes dephasing continuously like this. Afterwards, it is completely dephased. That does not end that. This process keeps on going. This dephasing, the spins start moving like this. They move like this and then come back and go like this. These spins move like this and go back and move like this. This dephasing continuously will be going on. It is an oscillatory function. Understand? Dephasing is an oscillatory function. At the same time, that intensity, the signal intensity, because of the vector addition, will become less and less and less. So the intensity is maximum and then start decaying like this in an oscillatory fashion. This is what we discussed in the wave pattern we discussed earlier, which you can represent in a circular manner. Exactly like this is an oscillatory function and also getting damped with time is a decaying function. Okay, this follows exponential again. And the time which requires for the spins to completely undergo dephasing is called T2. It is a type of relaxation we call. The spins are relaxing. In the XY plane, the complete decoherence means it is relaxing. This time required for this is called relaxation time. This is also called transverse relaxation time, or in other words, also called spin relaxation. Why it is happening? Why they are decaying? Why undergo decoherence? Because the spins are interacting with the surroundings. As a consequence, they lose phase coherence. That's what is happening. So this time required for this to interact and to lose complete coherence is T2. That is of the order of few milliseconds to seconds. Okay. Now what is happening? The spins are undergoing decoherence. But where are they? It has to go back. Signal is still there. But ensemble average, you can take the average of vector addition, you take completely, we discuss random phase approximation. Vector addition is 0, but the magnetization is still there. But it cannot stay there. It has to go back. Its original position was z-axis. It was along z-axis. By applying the pulse, we brought it to x-axis. That means we perturb the system. System is in a non-equilibrium state. The spins which were in equilibrium, we created a non-equilibrium condition. They want to still go back and attain equilibrium. Okay. Again, this is another type of relaxation. The spins which were disturbed slowly relax and go back to z-axis. What is the process involved? Again, it is interaction with the surroundings. The interaction with the surroundings for that process of decoherence and for this are different. Understand? So the time required for this to slowly come back and completely reach the thermal magnetization, which was there before the application of the RF pulse along z-axis, is called T1. T1 is the relaxation time. Also, it is called growth along z-axis. It is also called longitudinal relaxation. Z-axis or growth is z-axis is a longitudinal axis. It is also called growth along z-axis, longitudinal relaxation, or in other words, this is an energy exchange interaction. It gives energy to the surroundings, first giving its energy. Okay. To what are the surroundings? It is a lattice. That is why it is also called spin lattice relaxation. So slowly spin return to thermal equilibrium and after a time constant T1 and come like this. First we brought and they started undergoing decoherence. Here T2 was there and simultaneously, see the vector components here. You take the addition of this along z-axis, total sum of the vector addition. Okay, all of them if you add up, this magnetization is this much. But now you see where now lot more components are present here. You keep adding, the intensity is going up. Now vector addition is more. Magnitude of this vector addition is much more than this one. See this arrow, which is much smaller. I'll clear it. You can see this arrow, black arrow, thicker one. This intensity magnetization is much smaller. Now it is bigger. And after some time, what happens? Slowly, you reach thermal magnetization, mz, which is called m naught, which was what it was before application of RF pulse. This is the magnetization that was before the application of RF pulse. Okay, so this is what happens, and the growth again follows an exponential. Similarly, when we saw the decoherence, the decay was exponential. Similarly, growth is also exponential. Very interesting thing. So now, both these phenomenon happen simultaneously. They are not exclusive processes. In reality, when you want to detect the signal, this is what we are doing. Okay, we start collecting the signal after the application of the 90-degree pulse, create the coherence. Coherence starts undergoing dephasing and decoherence takes place. Signal and decay around the XY at the same time inducing EMF in the receiver and also undergoing decay, damped oscillation is there, and exponential decay is there. That is what is going to collect. That is called free induction decay. Remember, I gave an explanation for what is free induction decay earlier. This is exactly what it is. I just gave a expansion for the free induction decay, the word, what is FIA and D. But this is what is really happening. Pictorially, all these concepts what I explained was for you T1 and T2 is like this. Thermal equilibrium magnetization is along z-axis. Apply a 90-degree pulse, bring here. Temporarily there is statistical phase coherence and this is my receiver, and slowly phase decoherence takes place. At the same time, they start growing along z-axis. like this. Magnetization starts growing on a z-axis while decaying simultaneously in the transverse plane. It grows along z-axis, decays in the xy plane. And the decay follows an exponential like this, an oscillatory decaying function. This is the free induction decay we detect. You understand? This is what you do in your NMR experiment always. Now the question is, you may ask me, we applied 90-degree pulse and brought the magnetization here to z-axis. Should I have to always apply 90? What happens if I apply 180? Look at, if I apply for magnetization here, 180-degree pulse, I discussed about the pulses and phases earlier, I bring the z-axis magnetization to minus z. But here my detector is still here. When the magnetization was along that z-axis, in the equilibrium, I didn't see any signal. Same way, when it comes to minus z-axis, you will not see any signal here. 180 pulse will make the signal 0. You will not see any signal. Okay, I'll increase further. I'll take it here. You will see the signal, but in the opposite direction. See, this is where there is no, you can collect the free induction decay. That's what I'm going to explain now about the phases of the signal. I told you about the phases of the RF pulses. Now we'll discuss about the phases of the signal. So it does not mean necessarily you have to apply 90-degree pulse. I can apply 45-degree pulse here. Then what happens? If I apply a 45-degree pulse here, I have to resolve these components into Z and, into cosine and sine component, and you are going to detect this signal. See here, I will erase it. I have a magnetization here. Okay. Now I'll take the projection along this axis. And this is the component you detect. The intensity comes to, if you use less, instead of 90-degree pulse, if you use less than that 45-degree, your magnetization, what you detect, quantity is now less, intensity is less. You will get less signal intensity. Maximum signal intensity is only at 90-degree. Okay? You see what happens if I apply 5-degree pulse or 10-degree here. Okay, this is 10-degree. Now I take the component along this axis. See, this is very small angle, very small magnitude compared to this. So lesser the pulse angle, what you apply, you will get less signal. 90-degree pulse is the one which gives you maximum signal. Please remember that. So 45-degree also you can apply, no problem. But the only thing is, you have to take projection of that along the axis in which you are detecting the signal. That is the amount of magnetization you detect. That's all. Okay. So conventional one-dimensional NMR, this is what we do. Okay. Exactly what we do is this. Apply a 90-degree pulse and then put your receiver here in the x-axis. Bring from 90-degree x-axis or y-axis, doesn't matter. If you apply along x-axis, you will bring along y-axis, whatever. So you know how to understand this from the right-hand thumb rule. Then I start collecting the signal in the other axis. I am applying along x-axis, I will shift along y-axis, start collecting the signal. And I digitize and collect like this. It is an exponential decay, okay, and oscillatory. What we will do is, this has all the frequencies present. I am showing you it is only one frequency here. But in reality, it is not one frequency, which I explained to you when you understand Fourier transformation theorems. There are a number of such FIDs will be there. So many frequencies are present. Each of them will be oscillating its own frequency. The oscillation frequencies are different. So let us say if you have 50 peaks in the spectrum, there are 50 FIDs like this. They are all superimposed. Then it looks like an interferogram. Here it is easy. If there is only one frequency, what I will do is I will measure this and this. I know this is lambda, I can get the frequency, easy. But I have 50 peaks I will give you. You will get an interferogram. Then how do I know what are the frequencies present in that? It is not possible to identify like that. You cannot distinguish all the frequencies. But it is, of course, what I want to tell you is the signal we are going to detect in NMR. After all those things, we make some manipulations in the electronics, and the signal we are going to detect will be in the audio frequency range. Even though all the operation frequencies, everything is megahertz, finally the detected signal within the electronics, we do something, remove the megahertz component, we detect only frequency, the audio frequency range. Now let us say there are 50 frequencies and 50 sounds, different sounds are made. It's because it's audio frequency. My ears cannot distinguish all the frequencies. I do not know. If one person talks to me one frequency, if somebody says, I know what it is. If there are 50 people talking simultaneously at a time with different frequencies, I do not know what it is. So how do I understand? This is a mathematical problem. This signal which is collected in the time domain, if I want to know what are the frequencies present in that, we do a mathematical operation called Fourier transformation, which was given by pioneer in that area, Fourier transform, who gave this idea called Jean-Baptiste Joseph Fourier. It is a mathematical tool. We do this mathematical operation on this time domain signal and convert it to a frequency domain signal like this. Now, when I do Fourier transformation, it tells me what are the frequencies present, how many peaks are there, I know. That's what we have to do. Basically, this is what you do. Basically, what you do is you collect a signal like this. All these things you will not know. The technician will do for you. Put the sample, he will do some, give some commands. He will collect the signal. You will type a command to do the Fourier transformation. Computer does the job and gives you output like this frequencies. And this is literally what we are going to see. When we do the Fourier transformation, this is an equation for Fourier transformation. It is an integral function. This is if there is a time domain signal. Okay, this is the time domain signal. I can convert to frequency domain. I can do the inverse also. I can get the time domain signal if I have a frequency domain signal. So this time and frequencies are called Fourier pairs. If I know time domain signal like this, what I can do is I can do the Fourier transformation and then get the frequency domain spectrum. Take this time domain component to frequency domain components like this. Convert time domain to frequency domain. They are Fourier pairs. Supposing I am not satisfied with this, I will reverse Fourier transform, inverse Fourier transform. Then I get this time domain signal. So these type of operations can be done either way. This is a reversible operation can be done. I can collect the signal in frequency domain, take in the time domain, do this one, or if I don't want, I can take it back to time domain. So these are all in both the inverse operations are possible. They are Fourier pairs. This is all what you do in your NMR spectrum in the day-to-day life. In the routine NMR spectrum, this is what you are going to get. You understand? Send the pulses, collect the signal, and do some mathematical operation. Finally, what you are interested is to see the peaks, how many peaks are there. Then you start interpreting, depending on the frequencies present, what is this peak, what is this peak, what is this peak, to get the information about your molecule. That's what we are going to do. Okay. Now, after introducing Fourier transformation, I will tell you something about signal phase. Remember, all those things I hope you have understood. I know I applied an 90-degree pulse, brought the signal along x-axis. This is called MX component, magnetization along x-axis. My detector, my receiver is here. Now, what is the type of signal I am going to get? When I wanted to tell you one important thing I forgot here. When you do the Fourier transformation, the Fourier transform gives you real and imaginary peaks. It is like that. You get cosine component and sine component. Both will be there. Okay, when you have exponential here, I can resolve them into cosine and sine component, right? So cosine component is called a real component. Sine is imaginary. When you do the Fourier transformation and do the phase correction, etc., this you get a peak like this. This is called absorptive type peak, or you can get a peak like this. This is called a dispersive type peak. This is because of the imaginary part. This is because of the real part of the signal. When you do the Fourier transformation, this is what we always see here. But this is also present. Imaginary component is also there. This is a dispersive type signal. But we don't worry because we can get everything from here. We want only absorptive part. The difference is this and this is out of phase by 90 degree. Real and imaginary phases are out of phase by 90 degree. It is like cosine and sine. They are out of phase by 90 degree, right? Exactly. So this is what I wanted to tell you. Please remember, after the Fourier transformation of the time domain signal, we are collecting the signal like this. It is a real part. It is an absorptive type signal. There is imaginary part with negative dispersive type signal is present. We are not collecting that. Okay. So with that, we'll go back to the idea of what is the signal phase. I told you, now the signal is brought to x-axis and I collect the signal. Start receiving the signal. There is a maximum signal here. Now, real part is like this, cosine part, start with maximum amplitude because cos 0 is 1 and then goes like this. Okay, maximum amplitude. This is a cosine part. And you see the real part is an absorptive type signal now. They are exactly that is on the x-axis. And the imaginary part should be exactly here. So you get imaginary part is a sine part, starts with origin 0 and you get imaginary signal like this. Are you all with me? I hope you are understanding what I am trying to say. This is the real part and this is the absorptive real part of the FID, this imaginary part. Real part gives you absorptive type signal, this is a dispersive type signal. So now let us see what happens if we see, I asked the question, should we have to apply 90-degree pulse to get FID? You can have different also. What will happen then? First thing, magnitude of the signal is less because now I resolve into only this component and this component. I'm retreating only this component. So signal intensity is less compared to this. Fine, that's one thing. What next will happen? Look at this. Now there is a phase difference. If it is exactly here and the imaginary is exactly on the y-axis, the phase difference is exactly 90, real and imaginary. But now it is in between. It has a mixed phase. Phase for this is mixed. It has a mixed phase. So it is not pure real or pure imaginary or pure absorptive and pure dispersive P. Of course, the real component. The real component is not pure absorptive and the imaginary part is not pure dispersive. Okay. So this is what happens. Real part is not pure absorptive and imaginary part is not pure dispersive. There is a phase error here. You look at the bottom. Here, there is a phase error. See, this is what is called a pure perfect signal without any phase error. Here also, see here to here, there is a phase error. That's all what happens. You can apply pulse of any angle to collect a free induction decay. One thing is signal intensity will base. Secondly, you will get mixed phases. So this is what you have to understand. Pulse phase is one thing. Signal phase is one thing. Signal phase depends upon where is your signal and where you are detecting, where is your receiver. Signal phase depends upon where you have positioned your receiver. Okay, supposing I have positioned my receiver here in this case, what will happen? Same signal, I have positioned my receiver here instead of here. Then this imaginary part will be real for it and the real part will be imaginary for it. That's all. You understand? Depending upon where you have kept your receiver. This is why signal phase is very important. This is also called the receiver phase. These things are very, very important in NMR. The more often you play with these things, signal phase, pulse phase are very important in designing new sequences. Please understand these things. Okay? And as a consequence, I tell you, this is what it is. Now I am sitting here and they have a mixed phase like this. There is a phase shift in the magnetization. As a consequence, real and imaginary parts have a lot of, that's what you are going to get. Okay, let us take another example. What happens if the magnetization is here? Exactly what I said here in the previous example. Instead of putting the receiver here, I put the receiver here. Alternately, I put the magnetization here and put the receiver here. Both makes no difference. Now I am asking the same thing I am doing here. I am putting my receiver here. I am looking for the component of the magnetization along this axis, but the really magnetization is along this axis. Because I have applied the pulse in such a way, I have brought the magnetization to y axis. But I have not changed my receiver. The receiver position is here. Then what type of signal you are going to get? The real part is now out of phase by 90 degree. This is where I have to detect the real part. But it appears to be out of phase by 90 degree, real part. So what is happening? real part appears like imaginary or dispersive peak. It appears like imaginary and the signal is dispersive. Real part of the signal is dispersive type. What about the imaginary part? Imaginary part of the signal appears like real and the spectrum is like absorptive. It gets interchanged. You understand? Same thing. I said, if I sit here, now the same receiver I put here. What will happen? There is no change at all. The real phase is this, imaginary is this. They get interchanged. Real and imaginary gets interchanged depending upon where you are going to put your receiver. In this case, these are all the things you should understand what is the signal phase. Or when you want to identify, find out what is the signal phase, you should know where is receiver put in which axis. And then which is the phase of the pulse. Phase of the pulse decides which axis you are bringing the magnetization and where you have put the receiver, which axis you have put the receiver tells you which the signal you are detecting, whether you are detecting real signal or imaginary signal, that is dispersive or absorptive or mixed phase. That's what you are going to see. Now let us take the example like this. I have put the detector here, my receiver is here. My magnetization is brought to this axis. This is X, this is minus X. I have brought the magnetization to minus X axis. What happens? You are sitting here. Look at the signal, what happens? You are seeing the signal like this. That means real part appears to be real only, but it is negative in maximum. Signal intensity will be negative maximum. Same, there is no difference. Okay? Imaginary and real part remain same. But only thing is, the real part is negative maximum. When it is signal was here, it is positive maximum. When signal is here, it is negative maximum. What about the imaginary part? Exactly same. It should be opposite. There is no difference at all. Real and imaginary is real and imaginary same, remains same. But only thing is signal phase instead of positive, you get negative for real and imaginary also gets phased 90 degree or 180 degree like that. Yeah. Phase gets changed for imaginary also 180 degree. In fact, what happens if this is the type of signal you are going to get? In one case, another case, you are going to get signal like this. When it is out of phase by 180 degree. For this case, this is the type of signal you are going to get. You understand? The signal phase also now we understood. How you have to decide the phase of the signal that depends upon where you have put your receiver. Okay? The real phase is negative absorption, negative maximum you are going to get, and imaginary phase also is like this. These are all the things I wanted to tell you about signal phase. I hope you are all with me and you have understood. Today we discussed a lot about free induction decay, relaxation T1, T2, how the magnetization undergoes decoherence, how it decays in the X-ray plane, in the transverse plane, how it grows along Z-axis. I said both of them are exponential functions. One is a decay function, one is a growth function. Decay function is referring to transverse decay in the transverse plane. Growth pertains to growth along longitudinal axis, it is along Z-axis. And you collect the free induction decay, which is the oscillatory damping function as a function of time. You have to do the Fourier transformation to find out the frequencies present. While doing Fourier transformation, you know where you are collecting the signal. Accordingly, when the Fourier transformation has real component and imaginary component both, real part gives you absorptive signal, imaginary part gives you dispersive signal, and depending upon where is your receiver, you have different types of phases of the signal. This is all I wanted to tell you today. Okay. Next, I will discuss something about spectrum and line width. So, I think if I start that, and then I have to introduce to you something about selection rules, etc. It will take some more amount of time. So, what I will do is I will stop for the day. We will come back tomorrow, and tomorrow we will see more about the spectrum, transitions, what are the selection rules, what happens to the energy levels for homonuclear case, heteronuclear case, how do you get transitions, all those things we will discuss in the next class.